Hello and welcome. In this video, we will look at the ISO 15118 feature for electric vehicle supply equipment simulation, available with the 2022.3 release of Typhoon Hill Control Center. This feature allows you to simulate a complete charging station according to the CCS and ISO 15118-2 standard for smart charging and test interaction with any electric vehicle charging controller. As part of a combined charging system, ISO 15118 covers all charging-related use cases across the globe. This includes wired AC, DC, and wireless charging applications, as well as pantographs for charging buses or other large vehicles. By using this feature, you can now test ISO 15118 compliant electric vehicles for communication-related control issues, including potential security concerns. For now, this feature covers AC charging-related use cases on the electric vehicle supply equipment, or EVSE, side, as well as vehicle-to-grid and plug-and-charge capabilities. To demonstrate the ISO 15118-2 protocol feature, let's open Schematic Editor and drag and drop the ISO 15118 Supply Equipment Charge Controller component. ISO 15118 SECC implements the supply equipment side of the protocol, allowing the electric vehicle charging controller, or EVCC, to act as the device under test. This is important to note, since this component implements only the communication interface and not the controller itself. In other words, the component is used only to relay the necessary messages between the SECC and the EVCC. Should you wish, the EVCC could be implemented separately using signal processing components. The ISO 15118 SECC component works by passing signal processing signals to and from its terminals. By opening the Component Properties window, we can check the parameters required by the supply equipment, such as EVSE ID, supported energy modes, supported payment options, free service, metering, maximal delay, and station parameters. It is important to note that different terminals accept different types of values. Some use integer values, others use real, and others only accept states. For this reason, we recommend checking our component documentation for more information while parameterizing this component. In order to show a quick charging session, we will test the component with an existing EVCC application running in the PC. This is only for demonstration purposes, as the device under test could be replaced by any EVCC, or even a real ISO 15118 compliant electric vehicle using powerline communication. Let us add the input terminals as SCADA inputs and output terminals as probes, so that we can verify the communication session in the SCADA. We can also change the voltage and current rating from our charge station, as shown here. After that, let's compile and load the model to the Hill device. Finally, let's open the SCADA panel we prepared to check the charger controller communication. In the SCADA panel we have the basic widgets needed to verify protocol interoperability. The Request Energy Transfer Mode shows the requested energy transfer mode from the EV. The EV Maximum and Minimum Current widget shows the maximum and minimum current the electric vehicle can handle. The energy amount shows the maximum energy that should be transferred for the current session. Departure time shows the scheduled time for the charging session to end. EV maximum voltage shows the maximum voltage the electric vehicle battery can handle. In the CP state, or control pilot state, we can change the current state of the charging process. State C indicates it is ready to charge and state B indicates it is connected but not ready to charge. The PP state, or proximity pilot state, allows us to connect or disconnect the inlet plug from the EV to the EVSE. In the EVSE notification widget, we can force the charging session to stop for a renegotiation. Finally, with the RCD, or residual current detector widget, it is possible to force a fault by setting it to true. Charging only occurs when the RCD is false. With an EVCC running the ISO 15118-2 protocol connected to the Hill device through Ethernet or powerline communication, we can now run the simulation and check the charging process. After communication starts, we can see that AC 3-phase power is requested by the charging station. We can now also see the parameters requested by the EV, such as maximum and minimum voltage and current. The SECC then connects with the EVCC and starts the process of charging through ISO 15118. In the EV received message widget we can see the status of the communication from the EVCC. While charging, the EV charging status request message appears in the widget, providing a sanity check on the meter readings provided by the SECC. Thanks to these iteratively exchanged charging status messages, the EV has the means to check and validate the power drawn from the EVSE. At the end of the charging session, the EV sends the EV session stop request message and the SECC finishes the charging process. In this tutorial, we showed how to perform communication testing between electric vehicles and charging stations according to the ISO 15118-2 protocol in Typhoon Hill Control Center. By using this feature, you can efficiently use C-Hill real-time simulations to safely develop EVSE-related projects. Thank you for watching.